friends who are not here, remind them if they don't initial Tuesday, then they can explain to registration why they missed 2 classes. So I need your initial sometime this time on those papers, or next Tuesday. There are 2 lectures I particularly like in this course. This is one of them. The other is the last lecture in the course. Both of them are concerned with teaching you how great things are done. Most of the course is on this, but this particularly does it because you know I invented error correcting codes. You know error correcting codes are important, and I'm going to tell you as best I can how it happened. In order to bear some conviction that I'm telling you right, I will back up and tell you at Los Alamos during the war, I met people like Feynman, Metropolis, Oppenheimer, Bethe, Teller, Fermi. I saw that I was what you would call a janitor of science. Yes, you have to have people who do these things, but I certainly was not one of the ones who really mattered. I just kept the machines going. I was envious. I went to Bell Labs. I saw the same thing, that what I had done had been routine work, not bad, but not great. I started studying, even at Los Alamos, what was the difference? What was the difference between Feynman and me? Why did he matter and me not? I started studying the subject very carefully. So when I came to the point where I was creating error correcting codes, I was already extremely interested in the matter. Now I also knew one other thing. When you are up at bat, you think about hitting the ball. You don't think about how and style. That you don't worry about. You practice style other times. The same way when I was doing research, I did it. But as soon as it was over with, I stopped and asked myself, what happened? I was already in that habit. How did it happen? What happened? Now that does not mean that I tell you the truth. But by putting it into words very soon afterwards, I pretty well froze the situation. So I can tell you pretty much what happened at the conscious level and a slight probing of the unconscious. But I truly cannot tell you what happened inside myself because I haven't any clue as to how the human mind works. So I'm telling you, in some sense, a superficial view of what happened. Now, I was using this relay computer in New York, 2 out of 5 code, built by Stibbets, well, by Andrews and Samuels, but Stibbets had started this stuff, and this was for Aberdeen. And the machine had a very nice feature. Since it was error detecting, if an error occurred anywhere and 2 relays were not up, the machine would halt and retry. And the circuits were built so it would try 3 times, and if it could not get it in 3 tries, it concluded it couldn't get it, would drop that problem and automatically pick up the next problem. Well, in those days, I was a low man on a totem pole. I was just a visitor coming in and trying to use the machine for some useful work, and I didn't get much done. But the machine would run all night. So Friday afternoon late, they would mount a tape of a whole bunch of problems of mine, and the machine would work Friday night, Saturday, Saturday night, Sunday, Sunday night, and Monday morning I'd have all those answers. I'd take them back Tuesday to my friends at Murray Hill, and I'd give them the answers. So I was getting a great deal of computing done. Even if during the week I didn't get much, I got the whole lovely weekend. I came in one weekend, Monday, something went wrong, and all the problems were picked up and dropped, and I had no answers. I go back Tuesday and tell my friends, well, it happened, tough, I'll get them next week. Next week, the same thing. No answers. Well, I am moderately, say, provoked. Strongly, I'm very annoyed. And I say in slightly more polite words I'm going to use than I'm actually going to say, I said a little stronger than this, if a machine can find out where there is an error, why cannot it find out where it is? Because if it tell me where it is, I could change the bit from a 1 to a 0 or 0 to 1, and I'd be in. I want to stop. Notice one essential feature. I was deeply emotionally involved. I was aroused. It is characteristic of great things that the person involved is deeply emotionally involved. If you are simply, as many of my friends at Bell Labs were, content to just do things well, they never did anything great. The great stuff comes from people who care and care passionately. And if you're going to be going along, well, it's a good career, bing, 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 you probably will not do anything great. If you care greatly, you have a chance of doing something. So the first thing is emotional involvement. Well, let's go on. I had already, some years before, discussed the question of machines that could correct their errors. Namely, build 3 machines and build circuits to compare them and take the majority vote. Now, you don't doubt that this is the answer. So my question is, why can't a machine locate where there is error and correct it? I immediately knew it could. But who wants to build 3 machines and comparing circuits? Is there no better way? So that's the first question. How can I build a better method than 3 copies? Well, you remember last lecture I talked about parity checks. I had looked into parity checks extensively. I knew them intimately, and it wasn't very long before I said, well, if these are the information bits, and I put them in a rectangle, I put a parity check there across these rows, and down these columns, and if you want, this one also, it doesn't matter. Then, if there is one error, I will have the row, I'll have the column, I will have the coordinates. Pretty clever, right? Now, the closer this is to a square, since you've had calculus, the better. A long, lean one will have too much perimeter, right? A square will be the best. And I went through kind of things like, well, if I have 43, and if I add a bunch more dummies, I can bring up to 49, that's 7 by 7, I can get a nice square. So I was aware of these kind of things, and I was pretty content. I'd written what we call a pink on how one might do these things. Now, notice it fits my rule I've told you several times. I'll repeat again several times. Luck favors the prepared mind. I had gone through a lot of parity checks until I was anywhere, and you, I think, can see, with a knowledge of binary and knowledge of parity checks, this is not a profound invention. The calculation of this is the same so long as I use even parity checks, is not very hard. Well, next step. In order to get to New York, I could either take the train in the morning, or I could come to work about a half hour early, having reserved a seat on the company limousine, which went in to transfer mail from one place to another. I got a ride comfortably, usually in the front seat next to the driver, across North Jersey, through the tunnel, up to West Street Building. I'm in. So I'm doing it. Now, 2 things. One is, I will tell you again and again, the story you should look at the mistakes and learn from mistakes is basically wrong. You should review your successes. Because if you study the mistakes, when your chance comes, you will know how to make a mistake. If you study success, when your chance comes, you know how to make a success. Secondly, there are so many ways of being wrong and so few of being right, it's easier to study success. So I'm running through my mind these kind of things, and the North Jersey scenery isn't exactly something you want to look at. So I'm running this stuff through my mind, reviewing my successes, and out of nowheres comes the idea, if I put them in a triangle, and if I put the parity checks, just along the diagonal, I will have less perimeter for area. Now, I've looked in vain for whatever made me think of that. Why, reviewing the thing, did I think of a triangle would be better? Well, I am humiliated. I had been telling myself how great it was and how a square code would be the best possible. Here is a better one. Right then, I say to myself, Hamming, you're going to have to find the best possible code. No more finding a good one, think is real good, the best possible. Well now, if I go to a cube, and if I check all the ones across that plane by this parity check on this line, and I check the ones on planes that way on one edge and the ones that way on one edge, I will have the 3 coordinates. And so for roughly a cube of n by n by n, I'll have roughly 3n check bits for n cubed, which is a hell of a lot better than 2n for n squared. I'm a mathematician. If 3 dimensions is good, 4 is better. Now, I don't have to build a thing in 4 dimensions. I don't have to wire it as if it were 4 dimensions. Well, 4 is good, 5 must be better. And shall we say 10 miles, and I've come to the realization that 2 by 2 by 2 by 2 is really good. A nice cube. There will be n plus 1, one along each edge, and a 2 by 2, and 1 in the corner and 1 on each edge. So there's n plus 1 check bits for 2 to the nth. 2 to the nth bits in total, n plus 1 check bits. Okay, sounds real good. We're now up to about the Lincoln Tunnel. How will I prove it is best? How will I prove it is best? Well, one of the methods of dealing with those kind of problems is counting. How many syndromes can I produce with n plus 1 check bits? If I get n plus check bits, I can produce 2 to the n plus 1 various numbers from the n plus 1 check of bits. On the other hand, how many do I need? I need 2 to the nth for each position of the cube plus 1 for the right answer. I'm off by a factor of 2 approximately, right? I have not got the best code because you can see why if every one of these patterns, which I will call a syndrome, whatever pattern of check bits come up, if one pattern represents one position and one position represents one pattern, that must be best. And if I haven't got it, it cannot be best. Well, the car arrives at the door of Bell Labs. I get out, I've got to go in and sign in, and I've got to go to a conference. And that's the end temporarily. Some days later, I get back to it. What am I going to do? Obvious. After some thinking, if I make that syndrome tell me what position it is in, the syndrome shall name the position. The syndrome, remember, is a pattern of illness. It's the pattern of bits coming up. With all zeros meaning the correct answer. Otherwise, if an error in position 6, the binary number 6 shall come up. You can't beat it, right? How do I do it? You think a bit, it's perfectly easy. Look at the binary numbers. Every time there's a 1 in this column, the first parity bit must come up. In other words, the first parity bit must be 1, 3, 5, 7, 9. The second parity bit must be where 1 is net column. 2, 3, 6, 7, 10, 11, and so on. The third bit, the third parity check, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on. Is it clear that if I'm going to have the syndrome name the position, those positions which have a 1 must trip that one. Those which have a 1 there must trip that one, and so on. So that must be the rule. All right, let's do one. Take it out of empty space and look at a careful case. If I choose the most degenerate case, 3, I simply have send a bit 3 times, take majority vote. So I'll take the next one, 7. Check bits, 3. Those are the 7 positions. Now, my check bits, these are my parity checks right over here. 1, 3, 1, 2, and 4, I'm going to pick as the check bits. Because they have the property that they are set independently of anything else. Any other choice, one of the numbers may occur in several places, right? And that'll cause some trouble. Okay, so I've got 4 message positions. What message do you want? 4 bits. What do you have? Give me 1, 0, 1, 0. That's the message. Okay? I got to get it to you. First, I've got to put the check bits in. 1, 3, 5, 7. 1, 3, 5, 7. I have got to put a 1 in, right? Correct? 2, 3, 6, 7. I've got to put a 0 in. 4, 5, 6, 7. I've got to put a 1 in, right? Correct?
For even parity.
Huh?
For even parity. Even parity?
Yeah, even parities. Now, I'm going to change, say, the 5th bit. So what is going to be received by you is 1, 1, 1, 1, 1, 1, 0. What do? You calculate 1, 3, 5, 7. No. 1, 3, 5, 7 is odd. 2, 3, 6, 7. Yes. 4, 4, 5, 6, 7. No. What binary number is that? Change the 5th position. Strip off the check bits, and you've got the correct message. Right? If you look whether it's these bits or this or this or that, it does not matter a difference at all what place you put the error. I will always be able to correct the error. I send it to you along with the parity checks. You receive them, you apply the parity checks. If there's a single error, that's where it is. Simple? Obvious? Now let's say some things. Whether I use 0s or 1s, and in code developed, whether I replace 1s by 0 or 0 by 1 in any one position, it's the same code. If I change the columns around, so long as you and I agree on the change, it's the same code, right? So you might very well want the 1, 2, and 4 to lead first, and the 3, 5, 6, 7 be sent later on. This particular code is one realization with a very cute property of this. The syndrome names the position, but there's a whole bunch of equivalent codes which are the same code with trivial changes. And you might very want, for practical engineering, a slightly different code. Now, this is about as best that you can do. Now, that doesn't look good there, but if you look at a message of length, total length, 2 to the n minus 1, I have n bits. And so I have 2 to the n minus 1 minus n message. All right. Well, I have n bits. Now, if I take n equal 10, I have 1024 minus 11, 1013 for n equal 10. For 10 bits, I can send 1,000 message positions. For 3 and 4, it's unfavorable, but I have to write small codes. For a big code, it's evidently, I get a very favorable excess redundancy. I've only added 10 extra bits and covered 1,000. Right? So the one I put here is misleading. It's too easy and too simple, but I don't want to write out 1024 positions or 1023. I'm not about to do it in class. But you see why it's going to work. But if I go to 1023, of course, a double error. Now, in a double error in the rectangular code, let me show you what happens. If I had a double error here and here, I would get those two and those two, and I would not know whether that pair or this pair. Or if two of them were in a line, I would know the two rows, but I would not know the column. So this could not cope with a double error. Nor can this. If there's a double error, it will fix the wrong position and put in a triple error. So you ask yourself, what could you do? And Hamming says, well, being familiar with the binary system, he says, put on an 8th position, which is a parity check over everything. Well, now the situation is very easy. If the syndrome is all zeros and this is 0, the parity check is 0, you're in. If this is all zeros, meaning there's no error occurred there, but this is a 1, the error must have occurred in the 8th position. If there's a pattern here and a 1 there, there must be one error. If there's a pattern here and a 0 there, it must have been a double error. Therefore, for 1 extra bit, I can detect double errors. And it's a natural thing to add on. Same way over here. The same argument will apply. One parity check over everything, and I will know whether it is a double error or a single error. So 1 extra bit, and I buy a double error detection, which is probably a prudent thing. Now, let's not get confused about how fast I did these things. And I'm going to give you some more about what I did. I do not know length of time, although I suppose it could be dug out if you really wanted to. But my impression is it's something like 3 to 6 months' time. Remember, I was part of Bell Lab's team doing things. I was running computing numbers for other people. I was programming. I was doing all kinds of other things. I had a job of member of a team to do. This work was by and large done at home at odd moments. That's how you first get started. When you hire a plumber, you don't hire the plumber to learn on your time. You hire a plumber who knows. And when you're first hired as a researcher, you're told pretty much what to do. When you've demonstrated your ability to do research, then they give you freedom. And it's, in some sense, ridiculous. Again, jumping out of order, consider the situation myself. During this time, I was loaded with many, many other tasks. By the time the error correcting codes appeared, which was delayed for 18 months or so by patent troubles, and I gradually became famous, management gave me a vigor for your hand. And when, after 30 years at Bell Labs, I had the corner office with windows in 2 directions, a rug on the floor, a secretary, unlimited travel expense, and no assigned duties. But I didn't have any more ideas. When you're young, it's when you have the ideas, and that's when you are burdened with other things. The ground rule, as I say, is very simple. You must, on your own time, demonstrate greater ability, and when you've demonstrated that, they will give you the freedom to do it. But they won't, by and large, give you the freedom to do. For example, it's no use going to your boss and say, hey, I want some time to do some research, because I remember what happened when I was a graduate student in Nebraska. An instructor went to the head department and said he'd like to be relieved of some teaching so he could do some research in mathematics. The head department looked him in the eye and says, when you've done the research, I'll relieve you of the teaching. That's the way things are. And that's the way you want it, don't you? So your first successes must be done by this extra effort, this doing more than is needed at all times, and finally, when you do get some successes, then you've got more leisure, apparently. Now, of course, as you rise up the organization chart, you get more duties. That's where I was smarter than most people. I saw very early that Bell Laboratories would ultimately have a vice president in charge of computing. When I said it to people, nah, you're crazy, computing's always just a minor thing over here. But when I left, there was a vice president. And somewhere along the way, I said to my wife, you know, dear, I could be vice president of Bell Labs if I wanted to. And you know all the perks comes along with being vice president, you know, limousines and all kinds of other things and fancy this, that. I said, you really interested in the matter? She said, no. I said, neither am I. I'm going to avoid promotion. And so I spent my life avoiding promotion. It was a bit of a struggle, but I did it pretty well, although several times they promoted me in emergencies, and I had to get out of it somehow or other when the emergency was over and remind me, hey, the emergency's over, I want out, because they were going to leave me there. I cannot answer the question you may ask about that point. Would I have been more valuable to society had I risen to be vice president, since I thought then, and I still do, that I was practically the only one who understood the role of computers? Was I shrinking my responsibility, or was I playing to my greatest strength, namely originality? I don't know the answer, but occasionally, once in a while, I think, maybe I should have done the other one. Not that I want to be vice president, but maybe I had some obligations to do that. And the same way with you. As you go up the line, although you think you have more freedom, it seems like it, there's more darn things to be done, and it's not clear you have as much freedom at the top as you did at the bottom. It just looks like that. Well, let's get back to this business. Now, I've got those parity checks all right. Now, you learned one other thing. When you took analytic geometry, you learned that you can look at a problem algebraically or geometrically. And what I've given here is basically an algebraic approach. The fact is, after a little while, they were done somewhat in parallel. So let me draw some of the geometric aspect. A distance function between 2 points has got to be positive. If the distance function x, y equals 0, then x must be y. If there's no distance between 2 points, they must be the same point. Distance x, y must be the distance y, x. The distance from here to there is the distance from there to here. And lastly, the distance x to y plus the distance y to z is greater than or equal to distance x to z. If instead of going there, I go someplace else and there, it has to be at least as far as going there directly, right? This is what you mean by a distance function. This is something I learned when I was taking abstract algebra. Okay, I am going to look at a geometric picture now. Here's a cube. Now, I've actually drawn a two-dimensional figure, but you think it's three, because you can see it. This is a point 000, 001, 010, 100, and this is a point 111. And you can assign the coordinates all the way around. Now, going from one point to another is making one error. If I go along this edge and that edge, I have made two changes, right? Well, Hamming says the distance is the sum of the differences. Not the sum of the squares a la Pythagoras. Pythagoras says the sum of the squares of the difference is the square the sum of the squares of the difference on two sides is this the square of the total distance. Hamming says no. In what we call L1, it's a well-known mathematical formulation, which is abstract. This is the true difference. Well, if I put a message here, and a message here, a message here, a message there, then I say it is evident that every point is 2 away from every other point. And I can draw a sphere of radius 1. What do I mean by a sphere of radius 1? All points of distance 1 away are this. A sphere of radius 2, all points 2 away. A sphere of radius 3, all points 3 away, right? Well, if I have the property that the minimum distance, well, I better put it over here. I better put it over here. Pick a table. If the minimum distance is not 1 away from 2 points, I have 2 points with the same, 2 different meanings for the same point, I'm stuck, right? If the minimum distance is 2, I have error detection. Because if the distance is 2 away, you make a mistake, or I'm sorry, a message comes to you with 1 mistake, it's no longer a legitimate message, correct? Right? You can recognize. Now, 2 of them, you're dead. But 1, you're right. Okay. Now we go to 3 dimensions. Minimum distance 3. If the minimum distance is 3, and the spheres don't overlap, 1, 2, 3 is the distance across. I spread out the distance along a line. 1 error will carry me there, or 1 error will carry me there. If the minimum distance is 3 and you receive a message with 1 error, it is closer to one particular message where it came from than any other one. It is error correcting, correct? If the minimum distance is 3, 1 move away will leave it inside the sphere of radius 1. From the other one, 1 sphere of radius 1, in or on the surface. Therefore, minimum distance 3 tells me that if I can pack the spheres in n dimensions with that distance function, so the spheres don't overlap, I have error correcting code if and only if. If the distance isn't that much, then 1 would carry another one and you wouldn't know which one it was. Well, distance 4. 1 correct plus 1 detect. 5, 2 correct. Because if the things are 5 positions away, a sphere of radius 2 and a sphere of radius 2 will have no points in common. If you get a message from me and there are 2 errors and they're all 5 away, you can determine which sphere it lies in and which the message was. Correct? Right? Double error detection. Double error correction requires a minimum distance 5. It requires it and it is sufficient. 6, 2 correct plus a detect. 7, 3 correct, and so on. Whatever amount of correction you want, if you want k error correction, I must have those spheres of size 2k plus 1 about the message points with no overlap. It's a problem of finding non-overlapping spheres in the space with that crazy distance function. Correct? So you see that higher order correction codes can exist up to any amount you want. How to find them is another question. I answered the question for those. For minimum distance 3 and minimum distance 4, that's 1 correction and 1 detection. That was the extra bit added on. With this distance function, L1, the sum of the differences. So you see the geometry and the algebra. Now I can give you how many spheres there are. The whole space has two nth points. There's a center, there's the binomial coefficient n1, one away, and the n2, c, n, k. That's the volume of a sphere of radius k. That's the total one. Divide this by this, and you must have an upper bound on the number of spheres. Because this is the volume of one sphere, that's the total volume, divide total volume by spheres. I cannot do better than that. Now a perfect code is one in which every point is in some sphere. And once you get beyond the ones I gave you there are very, very few, in fact only a couple, perfect codes where you get every point. So there's some loss as you go higher. On the other hand, you do better. Higher error correction, shall we say, it defeated me. I tried and couldn't find any regular method. I could create isolated codes with a minimum distance, but I could find no regular method of doing it. But then, let me remind you another thing I'm going to tell you. I've told you frequently I managed my career. I had observed already people like Einstein. He had a lot of good ideas. He had a unified field theory. And for the last half of his life, he did nothing. I saw Shannon, other people. I saw that a great many great people do something great and they spend the rest of their life on that thing. And they do nothing creative after that. They add, elaborate, and so on. They become the great famous name for that, but they really do nothing else. Knowing these things, once error correcting codes were reasonably launched, I told myself, Hamming, you are not going to read papers on the subject of error correcting. You're not going to referee papers. You're not going to do anything. You are going to try, go out and do something else. I did that. I had the nerve to try that. Now it takes nerve. You're a great expert in the field. You're the name. You're going to abandon the field to somebody else to start back where you know nothing. It's hard to do. But if you don't do that, you will then do one great thing and that'll limit you. And it's very, very characteristic of great scientists. They do a great many good things, they finally do one thing great, and they spend the rest of life elaborating that. So I didn't. I managed my life by consciously and deliberately changing. I'm telling you how to do it. Well, now let me talk a little bit more about this L1. And there's another one, L infinity. L infinity, which is minimum max difference. Take the maximum difference in any two coordinates and take the least of that. And that's the maximum difference. I want to be outrageous. I said the other day exactly the same thing. I'll be outrageous again on the same speech. Pythagoras was the first great physicist. He found we live in L2. That the sum of the squares of the sides gives you the square of the diagonal of a rectangle. Hamming, in some vague sense, is Pythagoras Jr. He says, yes, Pythagoras is right about the physical world. No about the mental world. The difference between two strings of bits is the sum of the differences. It's not the sum of the squares. This is the correct way, or that. And I'll give you some examples. Somebody's coming down the street, a child. Is it your child? You may say, no, it's too tall. You are using L infinity. One difference is sufficient. You may say, look at all these differences. There's 6 different differences, that's why it's not my daughter. You're using L1. We have found, particularly in artificial intelligence, that L1, the sum of the differences of two patterns, is better measurement than L2. Sometimes L infinity. One single feature is sufficient to tell you it isn't that. So what had happened here is quite simple. Now, I leave it to you to think about the story. How difficult was it for me to say, well, I don't believe in Pythagoras. I believe in this crazy theory I heard about in some algebra course that I really want to work in L1, the sum of the differences. Yeah, when you say it, obvious. But before you say it, how obvious? Yeah, not so easy. There were several other things I told you, not so easy. But don't get the impression that what I have told you in, well, actual stuff, without the frills of how I did it, something like 25 minutes. Let's shall we say it took 50 days, or maybe 100 days. Thinking odd moments here, there, and yon, blundering this way and that way, but coming back again and again to the idea. Until I had what I consider is the best possible proof, but I also had the failure. I could not find systematic methods of creating 2 and 3 distance codes. Now those are the ones used heavily now. Now I did find, although I didn't publish, what are called burst codes. You simply break the bits up into a burst because lightning strikes and a whole bunch of bits are out, or there's a scratch on the disk, a whole bits are out. Well, what you do is you separate the bits far apart and you put them in codes separately, and you encode them in error correcting codes, so any single one of those far separated bits will be corrected. So if there's a string of them, as long as the string of errors is not bigger than what you're breaking up, you'll be able to find all the errors. Some of the consequences. Take the problem of digital music. A Japanese president of a company said to his employees, I want digital music because it can correct errors and get it high. And what I demand is this particular symphony that my wife and I like, runs 120 minutes. There shall be no errors, because one error can produce a blip. No errors in 120 minutes. They put in a Hamming type code with frills around to get around bursts because there might be a scratch locally. And that's why you have digital music. Simply the idea of keeping the signals far apart and coping with noise. It has had profound representation everywhere. Your discs write in error correcting codes and pull them back off in error correcting codes. You don't know it. You don't need to know it. We built machines error correcting so they can correct their own errors and go ahead, which is what you want. When you put a vehicle out on Mars to run it with a computer, you can't send a repairman out. You want these kind of things, and this is how you can do it. And the underlying theory is this geometrical picture, which is easy to understand. Those minimum distances are necessary and sufficient. How to find them is a very elaborate, difficult process, which there is not time to go into. But I say again, I did it in 3 to 6 months. I don't remember just how long. I could look it up, but let's say it took me 6 months to do it in odd moments. What the hell? There's weekends, there's evenings, there's lots of odd moments. There's while you're cleaning your teeth, while you're walking to work. There's all kinds of odd moments. It isn't so much to have done that like the time. As I told you, I was going to do. I'm willing to stick my finger at any one of your faces and say, are you prepared to stand up and say that given the position I was in and given the extra effort I made, that you could not have done it? Are you willing to point to any one thing you could not have done? Bunch of chickens. That is saying effectively that you are just as capable as I am. The difference is that, this phrase I've used several times, luck favors a prepared mind. I was prepared. I had looked into parity checks. It was not surprising I could think of this rectangular one. When I found it wasn't best, by that chance, I cannot account for it. Why the triangle? I cannot account. But once that was out, then only honesty is all. What will be the best? It's not sufficient to find a better one. Hamming, you got your pride. What will be the best code? Well, once you phrase it that way, you were driven right down the path that I went across here to exactly those parity checks and this method of doing it. Now, the method is not exactly new. It was, in fact, on the top of some breakfast food cards, the same kind of a code. You picked out the cards which had your birth date of the month on them. and you handed it to the other person. It's various dates around here, lots and lots of dates. All he did was look at the binary encoding and give you the date. Just what I did. Same kind of code. So it really was not new, but I didn't know it. I had to sort of invent it. I had to do these things. It was, I will summarize the points. Emotional involvement first. If you don't care strongly, you are not likely to do really great things. Secondly, prepared mind. You did more than the minimum so that when luck came around, you knew how. Another rule I told you, study successes, not only your own, but why did Galileo do what he did? How was Newton led to it? How did General so-and-so do such and such and so? The examination of successes will prepare you to succeed. The examination of failures, while I don't say you should never look at failures, will by and large prepare you to fail. So, furthermore, as I said, there's so many ways of being wrong and so few of being right, it's much more economical to study success. Now, I'll give you part of the same lecture, the last one in the class. Meanwhile, I will tell you a very simple thing. We'll call the class off. It's a very simple observation. Nobody ever told me the things I've just told you. I had to find them for myself because I was aroused that I was just a janitor of science who was never amount to anything beyond routine guy. Publish 20 papers or something else, but none of them would have mattered. I decided I wanted to be something different. I set out to do it. I did it. And if it wasn't Arikretnikos, there's a Hamming window out, there's various other things lying around that were named after me, so it was not a matter of luck. Yes, it is, but unfortunately for your argument, it's luck, all luck. Einstein did too many great things, Hamming did too many good things, various other people did too many good things, Shannon did Boolean algebra as well as information theory. Most great scientists did more than one thing, although some of them, as I told you, sterilized themselves by, once they hit on a good idea, pursuing it forever. It wasn't that they couldn't, it was they did not manage themselves. What I am preaching is, me having told you how to be great, you have no excuse, but you must manage yourself. I have an excuse for not amounting to anything because nobody ever told me. I have told you in detail how it was done. And you've been afraid to say, no, I'm not that smart. What you have to say is, either I didn't have the energy, I didn't do this or that, but luck, there's too many opportunities around everyone that you will not find one or two to seize and become great. And once you become great, you get the corner office, the rug on the floor, the secretary, the unlimited travel, everything else. But of course, I told you, in research, by the time you got it, it's too late. See you Tuesday. Somebody's got a list of signatures. Oh, here it is. Right. Thank you.